Hey, good afternoon, everyone. Welcome to the Inno Carnival 2025. This is Martin Law, your MC for today's webinar. Organized by the Innovation and Technology Commission, Inno Carnival is one of the highlights of Hong Kong's annual innovation and technology events. This year's theme is very special. This is INT Unlocks Your Dream. Supported by more than 50 partner organizations, Inno Carnival brings you a diverse range of interactive activities and inspiring webinars. Today, we are very pleased to have invited Dr. Gao Teng to share with us. Dr. Gao Teng is the CEO of Microelectronics Research and Development Institute, MRDI. Dr. Gao will be presenting on the topic of fun facts of semiconductors. Before we begin, I'd like to remind everybody that today's section is simultaneously live streamed on Zoom and YouTube as well. If you have any question during the webinar, please feel free to send them via the text to us. So if you are watching on the Zoom, please use the Q&A function below. If you are watching on YouTube, please use the live chat features. And also, please, again, feel free to text in your question anytime during the webinars. I'm sure our speaker will be very happy to answer them during his talk. So without further ado, let me pass the stage to our honorable speaker today, Dr. Gao Teng.
Thank you, Martin, for the introduction. It's my honor to have the opportunity here to do some presentation about semiconductor. I know semiconductor for most people, it seems to be very advanced or very complicated. And sometimes they thought it was so difficult to understand it. But I'm trying to use a very general language to explain to common people to better understand the semiconductor and to see maybe you or even your child would have the chance or interesting to explore more or even to have a career in semiconductor industry in the future. So this is my presentation. All of the graphics are coming from the internet, but I think I might inspire some of you during my presentation. I'm trying to make it a fun presentation, not a very boring technical presentation. Okay. So the first thing is actually the purity in semiconductor is very critical and very important. Probably you also already heard about the very fundamental material called the silicon. Okay? The wafer was made. It is a material called the silicon. And this is how we make these kind of silicon wafers. Okay? From such kind of very big bulk of material, and we cut it in piece and polish it. But the most important is that in order to do this advanced semiconductor technology, this material had to be very, very pure. We can say this material actually is the most purified material in the university. Okay, so the purest material in the university. And please imagine this is the kind of purification we need to achieve. Also 99.9999999, okay, totally 11.9. And if you consider this kind of purified, it means that in the whole Earth we have like 8 billion populations. We can only tolerate one, which is different. One person which is different than the other 8 billion people. And this is what we human can achieve today, and we cannot find any place else in the universe which can be more purified than this. So this is already a very interesting knowledge, I think. Okay, so I would like to everybody to think about a question. Actually, what's the foundation, a fundamental function of semiconductor? A lot of people will say silicon. Somebody maybe says, as I mentioned, purified things. Or somebody may have no idea at all. I have a kind of different opinion, maybe different than even some of the semiconductor people here. So actually, I think this is the fundamental function of semiconductor. It's called the MOSFET, or you can simplify that. It's a switch, okay? But it's not a normal switch. It's a switch which can be controlled by electricity or by, I would say, by current, something like this. So in general speaking, all the semiconductor, all the chips, most of, I could not say all, but most of the chips like the CPU, the AI chip, the memory, they're fundamentally made by billions of such kind of switches. Why we make this kind of switches? And how to use it actually to do the calculation. For switch, it's just we want to make a different kind of we call the states. Right? We have switch on, we have switch off. But how to really come into a so complicated calculation afterwards? Please think about this. Okay, I'll give 1 second, and I have the answer here. Is that so? This comes to this 0 and 1. Okay, binary. People will think why we use binary when we study in the middle school. Probably a lot of people was wondering why we have to create such kind of a binary. Okay, it's not so convenient to use, to be honest. But actually, this is perfect system to transfer the switch into a very powerful chip afterwards. In most cases, this 0 indicated an off status, and 1 indicate an on status, a switch on. So in principle, if you can make a switch with controllable switch, you can also make a different kind of computer, different kind of chip. Okay. This is really, I think, the fundamental function of semiconductor. Okay. And of course, the semiconductor is happened here. Why it's called a semiconductor? It means that sometimes it's conducted. Sometimes it will not conduct it, so it means it will not let the current pass through. And how to change this kind of status is by this gate. Okay, you have a kind of voltage on it. You will create a kind of field. Okay, then it will change the material into a conductivity status, and that current goes through it. So that's really the fundamental function for semiconductor here. Okay, so maybe people are wondering what is the chip looks like inside this. So I just show you, this is a cross section of a chip. So this is really what we call the transistor, as I indicated before, the MOSFET. Okay, and these are the method to connect all these transistor to make it a functional chip afterwards. Okay, and then later on we will have a package just around it. And if you try to remove all this, we call dielectric material away and keep all the metal still remain, then you will see this kind of graphic here. It's copper, okay, made by IBM before. This is, you can see it's already very complicated, okay? A lot of metal layers try to connect millions or billions of devices underneath it. So this is what the chips look like inside if you really, dig into it. Okay, so in order to let you understand better what's the process of to make a chip, so I just make the copy one of this graphic from internet. You can see the bare wafer, as I mentioned, the very purified silicon wafer normally, and they make a deposition and they put a kind of photoresist. This kind of material is kind of light sensitive. And we have a kind of reticle layer on top of it. This layer will define the topographic structure underneath it. And we use this called a lithographic machine to expose it. And some of the light will pass through this reticle and make this photoresist change their function to either more harder or more easy to be removed. And then we can then remove part of this photoresist and then use them to stop, to protect this part during the etch step. And then they will create this called topographic afterwards. And then we might need to do some kind of iron implantation to add some different kind of atom into this material to change their functions or to make it kind of semiconductor material. Okay, and they will be repeated many times for these most advanced chips today, maybe more than 100 times. Okay, to repeat these kind of functions and to make different kind of structure within this kind of on top of these wafers. And then they were, of course, doing this dicing, bonding, and then testing, and then sell to a company like computer company or NVIDIA to install a kind of bigger machine to be used for AI, for example. Okay, as you can see, people always curious about this lithography because a lot of people are talking about this today. EUV, for example, now everybody, even cleaning lady, knows about EUV today. Okay, so I will spend a bit more time to explain what is EUV actually. It's very interesting because this EUV today is really the most complex machine made by humankind. Okay, I got a question here. Let me just have a look. Okay, I already got a question, but I think I will answer this later on. It's about the cost of a factory. Yes, this is a very good question. I will do it later on. Okay. Okay, so just try to show how complex is this EUV machine. This is the machine made by only one company in the world today, is by ASMA in Netherlands. As you can see, this is really a huge machine. Okay, and I have some data here. Sorry. So this machine, if you really want to install it, it's required 40 Boeing's 747 to transport all these components into the factory and to install it. And it takes at least 100 well-trained engineer to install this machine. And it normally take at least 3 months, maybe half years to make it work. And in order to keep this machine running, it still need a lot of engineering to stand by. Okay, so this is really very expensive machine. Okay, and for EUV, so this is called extremely ultra light, right? So they have a short wavelength. But it's kind of strange maybe for some people that if they know it exactly is a 13.5 nanometers wavelength. So why we choose this one? Actually, this is a long history. Okay, I just checked from website that it is about 40 years ago. Okay, there was a paper uh, answer the question or indicate that EUV might be able to fulfill the current function to make a smaller dimension of a structure. Why? Because everybody knows that light has this kind of wavelengths. So if we really want to make a small dimension structure, you need a smaller wavelengths. But once the wavelength is getting smaller, normally it means it will have more energy. And with such kind of short wavelength light, it's very close to, I would say, kind of laser, okay? And that is so high density energy that you are not able to use a normal transparency lens anymore to focus that, because it will melt down the lens when they do the transparent through this material. And people have to think that they have to use a different way, right? Refraction, okay? That means you need to create a mirror to do reflection. But such kind of wavelengths also can be easily absorbed by any kind of material. Even in the air, it will degrade very, very fast, okay? So people have to think a way to reflect this kind of light in a vacuum system. So mirror is very important actually to make this happen. And the problem is that it can be absorbed by any kind of material, almost any kind of material. So there was a scientist 40 years ago found out that if we put two different material one by one, same film, one by one, they can have a very special refraction, which will have like at least 50% of efficiency to do this kind of refraction. And because of this discovery, so people realize that we had a chance to use this very short wavelengths to create such kind of lithography tools. So we need a mirror. And actually, there were two kind of material which can do the similar things. One is on the 30.5 nanometers. The other material is on even short one. But that material was so dangerous. It's kind of toxic material, very dangerous to be used. So then the engineer decided to use this 34.5 nanometers. And also because people found that there's a chance to create this kind of wavelengths, it's using a thin droplet. Okay, so the engineer create a system to drop a thin droplet in a speed of like 50 drops per second. And for each drop, it will have to pass through this vacuum system in a speed of 300 meters per second. This is kind of speed like a sun, okay? So, and during that period, there will be a laser light which should hit on this drop, which is only, I think it's 25 nanometer diameters, to vaporize this thin material. And then immediately another laser have to also hit this vaporized material to create this powerful source as a laser afterwards. So this is a very, very complex and very, very accurate process, okay, to be done. But we really did that. So we have this stable and a powerful source. Okay. And as I mentioned, the reflection efficiency should be high enough. Before we thought it was only 50%, but then after carefully calculation, the engineer noticed that it can achieve like 70% of reflection efficiency. And that should be enough for a complex system like this. Okay. So besides this laser, the source of the laser of the light, another big challenge is the stages, because you have put the wafer underneath it and you have to move your reticles fast enough to print on the wafer. Otherwise, we call the throughput will be too low, meaning that for every hour, you probably can only expose one wave. This is economically not acceptable in the industry. So normally the industry today, they can do like in 1 hour, they can process more than 200 wafers thanks to these very, very efficient stages. But in order to make such kind of stages, there are a lot of challenges here also. Give you an example. You have to move this kind of stage in a fast way. How fast it will be? The acceleration is 10 to 20 Gs. This is even bigger than the jet. Okay, the jet plane, they have to run very fast. But normally it's like a 5 to 7 Gs because if a human being is on that jet, this kind of acceleration, if it's too high, that a human being cannot tolerate. But for this kind of stakes, we have to make it like 10 to 20 G speed, this acceleration. Okay. Besides that, we have to make it very accurate because the dimension is so small. Okay. If we are not accurate enough, that this kind of small dimension will be useless. So they have to be in an accuracy of smaller than 1 nanometers and repeatedly. So just imagine that the two jet pilot, they all drive their jet in their extreme speed, and they're able actually to write a letter easily on the other's clothes. That is really amazing, okay, in the engineering point of view. Or I remember there was another example saying that you can drive a jet with its wing to write words in a hair, a very small hair, such kind of amazing results coming from this EUV machine. Yeah. Okay. Okay. I also would like to talk about this CMP, chemical mechanical polishing. This is another step. It's very interesting, or it's very easy for people to understand because we really need a very planized surface in order to, put a lot of layers on top of it. Today, the most advanced technology can put more than 300 layers on top of each other. Okay, and you have to be very planized because you have so much structure there. You will create kind of we call topography, and if you didn't do anything, the topography will become worse and worse, and it will cause a lot of problems on lithographic, also on other kind of process. So we need to polish it. And it's easy. You can understand that normally processing with, sand, for example, this kind of mechanic, but it will cause a lot of scratch there. Then we think, okay, we need to do some kind of chemical reactions to smooth that stretch to finally remove that. Right? So it's a combination actually of chemical reaction and the mechanic reactions actually. And this is very important today for these advanced tools. So every advanced nodes need these kind of technologies. And then the final result is also very impressive. Okay, so for such bigger wafers, normally the differentiation in the whole wafer will be within a few atomic level. Okay, so like less than 1 nanometers again. And this has been developed for the last, I think, 20 to 30 years, and we achieved this kind of results. And this also help us to solve another problem is that, if we want to connect this kind of device, we need to use metal, and we used to use aluminum. Right? It's easy to etch and to create these kind of aluminum lines just on top of wafers. But then we think aluminum is not good enough. We have to use copper. But copper is so hard to etch. It's too hard. Right? And then there's a smart guy from IBM actually. They think, okay, if we cannot etch them, then maybe we can polish them. Okay, so let's create so-called damascene process. Right, and these are the left side is the general we call etch process, mostly for aluminum kind of material. Okay, you can easily create these aluminum lines there. And then this called the damascene process is used for cup line etch. And then people are getting smart thinking that maybe we can not only make a couple lines, but also we call the vias between couple lines to connect the bottom couple line to top couple lines in one step. Okay, so this is what called the dual damascene structure, and they use the CMP to polish it and to finally create the line afterwards. And when I noticed this kind of technology, I was really impressed that these engineers are really smart to find out whatever solutions to fulfill their goals. Okay, let's go to this chip manufacturing. This is a photo of TSMC's fab, actually. You can see that these are tools, actually the same tools in one line. Why? Because for each tools, you only have limited throughput. If you want to increase your throughput, then you have to have same tools, and then you can expand your throughput faster. And also remember that be aware that on top of it, you will have called a kind of robot on track. Okay, these are the kind of track to automatically transfer wafers from one machine to another machine automatically. This is a full automated fab for chip manufacturing, and this is very common today for advanced factory today. By this way, although we have to invest a lot of money, but it's very high efficient. Okay, and you can see there's almost nobody in this clean room today because it's almost fully automatic today right now. But indeed, it's very expensive. This is a kind of factory is very expensive. The first thing is that the buildings itself with clean room, we have to keep to make a clean room has almost no dust at all. And also the facility to support them because we need to use a lot of chemistry, gas, liquid, and we have to be able to treat them in appropriate way, not to contaminate them, and to be able to run it in a safe way, because a lot of these material are very dangerous material, easy to expose. And also, of course, these tools are also very expensive equipment. And for example, the EUV tools today, it's one EUV tools, I think is like 200 million US dollar at least. Okay. And the latest tool, I think EUV tools in the new model is like 4 to 500 million US dollar per tool. Okay. And for a factory, you need maybe more than 10 EUV tools, okay, in order to have enough capacity. So this equipment require a lot of money. Okay, sorry. And also, as I said, we need a lot of raw materials. So these are also kind of expensive because they require purity. Okay, everything requires purity in this kind of fab. Let's see, make this. And also, of course, you need some engineering to maintain these tools because tools might be malfunctions, so you have to repair it in a very fast way. Okay, and in end, actually, we make a very cheap chips. How cheap it could be? So today, maybe for AI chips, it's kind of expensive. It costs you maybe several $100 per chip, but it's kind of bigger chip. But for other kind of chips, we can make like several cents per chip. Okay. And it's kind of joke inside some kind of industry that we semiconductor people, we did our best. We did a lot of effort. We spent a lot of money to make our products more powerful, but also more cheap than before. And indeed, that's true. And that's the reason we can enjoy our mobile phone, for example, every changes every 2 or 3 years, a new mobile phone without significant increase of price or even a decrease of price, and with much more function, much powerful functions afterwards. And that's indeed the big achievement from the semiconductor to keep the rest of this we call the information society running in a reasonable cost afterwards. Okay, so let me see if there are any questions here. Okay, there's an interesting question I can answer here. Does quantum computer require chips, semiconductors as well? Yes, definitely. The quantum computer, actually, the core is also we call the quantum chips. And they, of course, they're more advanced in a way that they use, normally they use different series, of physical series, to make these kind of switches, okay? And in principle, it should be much faster. For a reason that actually, if we don't go for quantum computer, we still rely on current, okay, which is electron, right? 电子 electron. An electron go from this side to the other side. It always takes time, okay? They cannot be uh, always faster and faster. So they have kind of limited speed. So today we try to reduce the distance from electron from here to there and to save time. But they will definitely have a limit afterwards. And then the quantum computer comes. They have different kind of physical phenomenon. So in principle, they should be faster, right? But anyway, they still need this kind of semiconductor technology, right? Actually, there's something which are not really we call a useful CMOS, or we call it the semiconductor or microelectronic. For example, for display, okay? But they still use similar tools, similar semiconductor equipment, same even. Why? Because with the technology developed in semiconductor, these kind of equipment become so powerful that they really can do a lot of amazing things. And the people on the other industry, like the display industry, they notice this kind of powerful equipment. So they tried also to use this equipment to do their products. Okay. And that's really the biggest contribution of semiconductor to the whole world. Okay. So I would like to also uh, maybe have more fun. Let me see the timing. Okay. I would like to leave a bit more time for Q&A. So I still have like 5 minutes. Okay. So to have more fun on this. So the clean room should be very clean. Okay. So there are data, but I think it's probably difficult for people to really understand how clean it is. As I say, it's 10K times cleaning than normal hospital operation room. Hospital operation room normally need a very clean environment, but the clean room for chip is need even more clean than this. And remember that that's also very important. It's always take times to build a fab and start manufacture. And this time normally is 3 to 5 years to build the facilities, to install the tools, to fine-tune the tools, and to really make the manufacture. Okay, 3 to 5 years. So that means big challenge for these investors or decision maker. Okay, you have to forecast what do we need after 3 to 5 years, right? And it's a risk, of course. Maybe you made the wrong judgment and you made the wrong decision, and after 3 to 5 years, you realize that you are going to manufacture something which are useless or not compatible at all. So that's a big challenge indeed for semiconductor. And also the whole fab need to avoid vibration because the fab equipment can only tolerate very small vibration. For example, for this kind of lithography tool, less than 1 nanometers. So that means that for the fab, you have to avoid a kind of, how to say, 跺脚, okay? Several months ago, 那个跺脚 might impact your machine. So we will have a lot of solutions, of course, to avoid these kind of vibrations. And also the water used in the fab is extremely pure, okay? It's 1 million times purity than normal water. So you are not able, you cannot drink this kind of water because it will harm your body, actually. It also costs more than 20 billions, normally US dollar, to build an advanced fab. What I mean, advanced fab means like 3 to 7 nanometers generations fab, okay? And then the fab also need to run 24/7. Why? Because it's too expensive, okay? If you don't really use this kind of facility in a more efficient, most efficient way, actually you are going to lose money. And the competition is so heavy. So everybody have to really run 24 hours every day and 7 days a week. Okay. Even during, Chinese New Year, normally the fab will still continue operation. Okay. If you are not able to fully use all your throughput, normally a fab will lose money for sure. Okay. And also the fab need to use more than 500 different chemical materials. Around 30 to 40% are dangerous materials, dangerous gas. Okay. So they have to really take good care, take very good care of everything. Okay. And also, and it's not because of danger, it also could cause contamination because every contamination will really damage the device, the chips. The temperature will be, failed afterwards. So the fab need to control not only metal, actually, not only metal contamination, but any kind of contamination, okay? But the metal contamination is the most critical part. And the metal contamination normally should be controlled below 1 part per billion. So means that for 1 billion kind of atom, you can only have one different kind of material. Right? And we need to always monitor this kind of contamination to make sure nothing serious happened afterwards. Okay, about the Moore's law. Okay, people knows about this Moore's law. And these are two graphic. This the first one actually is most commonly used. Okay, meaning that for every 1.5 year or sometimes 2 years, we will have one generation, or mean the transistor will be doubled in the same size. Okay. But I would like to talk more about the second graphic. Actually, this is a very original draw from Morse, this post Morse. And you can see it's a very interesting graph because it's a more information show here. Actually, it indicates that even for one technology, like the technology in 1970s, you have the optimized technology, like a number of components per integrated circuit uh, is like 1,000, then the cost will be the lowest one, which means that if you try to do something very hard, okay, to make more chip, more device in one chip, you can do that, but it will cost you more, okay? So people, when they're doing this kind of manufacturing, they have to find the optimized technology, okay? So this means that for semiconductor technology, you always need to think about we call opportunity windows. If you are too advanced, okay, you still have no market. If you are less advanced, you miss the market. Okay. If your technology are too good, that is too expensive. This is useless also. So it's a very complicated decision, but we have to always compromise between the technology's advance, the marketing requirement, and also the cost. Okay. And this is Moore's law, also technology note. the only message, because of timing limit, and the only message I want to show here is that we are talking about generation before, like 14 nanometers, 7 nanometers before. Actually, that indeed indicate the kind of minimum dimensions, okay, we can make. But today, it's no longer related to the dimension, minimum dimension anymore, okay? It's just a sign, a symbol to indicate different kind of technology node. In reality, the most important thing is actually for each node, due to Moore's law, each node should have some improvement. And this improvement means power, performance, area, cost. If you have like 20% of power reduction, 20% of power performance increase, and your area can shrink to less less than 20%, and your cost will be reduced 20%, you will have a new generation. Okay. And of course, timing is also important. You have to do it within a certain period. Otherwise, your technology become less value afterwards. Okay. To be honest, these are the real driven force for Moore's law. Okay, but still not the fundamental one. What's the fundamental one? The cost or money. Okay. In semiconductor, money or try to earn money is the fundamental or the real driven force for people to explore new area, to achieve new result. And that's the fundamental things. Okay. Okay. A final maybe explanation, because MRDI,香港微电子研发院, we are doing a third generation technology, semiconductor technology. Why semiconductor technology, and why they call third generation? Okay. Actually, third generation semiconductor is some kind of wide band material, such as gallium nitride and silicon carbide. They call third generation. They are not more advanced than silicon. They're just a different kind of material and a different kind of categories and different kind of advantages. Okay, and their advantage normally is called high voltage, high temperature, high frequency, sometimes a high radiation area. So they have this kind of advantages. So they are very good can be used for energy saving, for example. And that's their advantage. And I believe this is also a very good cutting point for Hong Kong to start rebuilding semiconductor capability. Okay.